is an electromagnetic wave, and an electromagnetic wave, for its propagation, does not require any material medium. Okay, electromagnetic wave does not require any material medium for its propagation. So basically, all the concepts we will discuss here. First, we will discuss what is the concept of displacement current given by the Maxwell. There was a scientist named Maxwell uh, who has given the idea of the displacement current, and that leads to the understanding of the electromagnetic wave. Okay, so first we will discuss that. So for that, before we should know what is the Ampere's circuital law. Just we are revising what is the Ampere's law, Ampere's circuital law. Ampere's circuital law. So Ampere's circuital law is, suppose this is a wire, suppose this is any wire, and this wire having a current I, this wire having a current I, and I want to find the magnetic field at this point. I want to find the magnetic field at this point. Suppose this is a point P. So what I will do, I will take a closed loop. I will take a closed loop basically. I will take a closed loop around this wire. This is the closed loop, okay, and this closed loop is passing from this point P where we want to find the magnetic field. Okay, so Ampere's circuital law says that if you will take the line integral of magnetic field, if you will take the line integral of magnetic field around this loop or along this loop, what is this? This is basically a wire carrying a current I. And what is this? This is the loop, Amperean loop, or you can say simply loop. So according to Ampere's circuital law, if you will take the closed integral, or you can say the line integral of the magnetic field, that is B dot dl, that is equal to mu naught times the current enclosed by the loop. Mu naught times the current enclosed by the loop. Okay. So basically here there will be some magnetic field due to this wire. Okay. Suppose this magnetic field is B, and this will be the small element dl. This will be the small element dl. This will be the dl vector. The direction of this dl vector is same as that of magnetic field here in this case. So basically, what is the Ampere's circuital law? The line integral of magnetic field, is equal to the mu naught times of the current enclosed in the loop. So this is the Ampere's circuital law. So basically, Ampere has given this law if to calculate the magnetic field at a point. Okay, suppose here we have taken a point P, and with the help of this Ampere's circuital law, we can calculate the magnetic field. We will see. Okay, but there was a problem in this law. That was found out by the Maxwell. Okay, so that we will discuss now. Basically, this is inconsistency in Ampere's law, in Ampere's circuital law. Okay, inconsistency in Ampere's circuital law. See, what is the inconsistency in Ampere's circuital law? Suppose I am taking a capacitor. Okay, this is a, these are the plates of the capacitor. Okay, these are the plates of the capacitor. This is one plate of the capacitor. Okay, and this is another plate of the capacitor. So it will be like this. Okay, plates of the capacitor are there. Okay, now it's fine. This capacitor is connected with some battery, is connected through wire with battery. This capacitor is connected with, this is a positive terminal of the capacitor, this is the battery, and this is a negative terminal. Here is the positive, here is the negative. And these are the two parallel plates of the capacitor. These are the two parallel plates of the capacitor. Okay. These are two parallel plates of the capacitor connected with battery. Okay. So now, if this capacitor is connected with battery, what will happen? Current will flow. Current will flow. This capacitor will charge. Okay, this capacitor will charge when you will connect a capacitor with battery. Then there will be the charging in the capacitor. Basically, I want to say there will be the current in the circuit. There will be the current in the circuit. There will be the current in the circuit. So now take one point. Take one point. Suppose I have taken a point here, and at this point, due to this current, you can imagine this as a current carrying wire. This is a wire in which there is a current I. Consider a point here. Okay, consider a point here, and suppose this point is x. Suppose this point is x point. So now consider a loop, and this is your point x. So when you will apply the Ampere circuital law to find the magnetic field at this point x, to find the magnetic field at this point x, so you will apply the Ampere circuital law. The line integral of magnetic field along this closed loop is equal to mu naught times of the current enclosed by the loop. So for loop 1, suppose this is your loop 1, and you are finding the magnetic field at x, at point x. So you applied the Ampere circuital law here. What is Ampere circuital law? Line integral of magnetic field is equal to mu naught times of the current enclosed by the loop. Okay, so now as this point and all the points on the surface of this loop is a circular loop, are at the same distance from this wire, so you can say the magnetic field value will be same. Magnetic field will be constant. We have done this in the earlier chapter. So magnetic field will be constant. So closed integral of dl. Okay. So first what we will do, we will open this. Basically this is written in the vector, so it will become v dot dl, and v dot dl into cos theta, and angle between the magnetic field and the dl vector is 0. I have told here the angle between the magnetic field and the dl vector is equal to 0. Okay, so here you will write v into dl into cos theta, and that is equal to mu naught into the current, and v is constant, and you can take out of the integration, close integration. Okay, and this cos theta is cos 0, and cos 0 is 1. So basically you will get this is equal to mu naught into I. What is close integral of dl? What is close integral of dl? Means this is closed line integral. This is closed line integral, means the length of this loop. Length of this loop is 2 pi r. Suppose r is the radius of the loop. Small r is the radius of the loop. Okay, so this is b into 2 pi r. B into 2 pi r is equal to mu naught into I. So magnetic field at point x is equal to mu naught I divided by 2 pi r. Very good. Very good. This is okay. No problem. No problem in the Ampere circuital law. Till here, no problem in Ampere circuital law. And for checking whether at this point there is a magnetic field or not, you have placed a device, magnetic needle you have placed. Okay, you have placed a magnetic needle. Okay, this is a needle. So this needle is deflected. This needle is deflected. So now it is confirmed that there is a magnetic field at this point x, and this is given by b is equal to mu naught I divided by 2 pi r. Till here there is no problem in Ampere circuital law. Till here there is no problem in Ampere circuital law. Now there is a current in the circuit. There is a current in the circuit. Okay, there is a current in the circuit. What will happen if I take a point here? Suppose I am taking a point here, and this point is suppose y. This is point y. Okay, and now I am taking a closed loop. I am taking a closed loop here. This is a closed loop I have taken, and this closed loop have the radius r, and suppose this is a point y. So now if I want to find the magnetic field at point y, suppose this is a loop 2. This is loop 2. Loop number 2, and we are finding the magnetic field at point y. So what we will do? We will apply simply the Ampere circuital law, that is line integral of magnetic field along a closed path is equal to mu naught times the current enclosed by the path, current enclosed by the loop. Okay, so all things will remain same. This is b, this is into 2 pi r, and this is mu naught. Now tell me what is the current enclosed by this loop. Hiba, what is your name? Nida. What is the current enclosed by this loop? This is a pure vacuum here. There is nothing here between the plates of the capacitor. Just fast, tell me fast. Hamza, you tell. What is the current enclosed by this loop? Nida and Hamza. Nida, do you know or you don't know? Very good, very good, very good. Zero, zero. Hamza, there is no current. See here, where is the current here? There is no current. There is no current here, na? Okay. So there is no current here. Zero. If you will calculate the value of the magnetic field at point y, then you will get 0. Okay, fine. But when you are placing a magnetic needle, here at this point y, and you are checking, here will be the needle deflected again. Needle deflected again. If the needle is deflected, means there must be the magnetic field at point y. There must be the magnetic field at point y. But according to this law, according to Ampere circuital law, there is zero magnetic field. But in actual, there is some magnetic field here. So what we can say, there is some inconsistency. There is some inconsistency in the Ampere circuital law. Obviously, we can say there is some inconsistency. Okay. Hamza, got it? This point? Hamza? Better tell me. Nida, got it? Okay. Hello, Fawaz. Hello, Fawaz.
Hello.
Hello, how are you?
Hello. Yes, I'm fine.
So today we are discussing the electromagnetic wave. Just I am recapping it. What I have told you, what I have done. Okay, I have told what is Ampere circuital law. Ampere circuital law is the line integral of magnetic field is equal to the mu naught times the current enclosed by the loop. Suppose this is a wire AB. Suppose this is your wire AB, and this wire AB carrying a current I, and at this point P, if you want to find the magnetic field, then you will apply this law and you will get the magnetic field. Okay, now we are discussing what are the inconsistencies in the Ampere circuital law. Okay, so what I have done, this is just the charging of the capacitor. This is just the capacitor charging by battery. This is the capacitor charging by battery. Capacitor charging by battery. If the capacitor is charging by battery, then there will be the current also. Okay, so here there is a current, and if I want to find the magnetic field at X, so I have applied the Ampere circuital law, I got this magnetic field. Okay, now at point Y I want to find the magnetic field by applying the Ampere circuital law, and at point Y I am getting the magnetic field value 0. But when I place the needle here, then in actual there is a magnetic field. So what we can say, there is an inconsistency in the Ampere circuital law. There is some inconsistency in the Ampere circuital law. That is why here the needle is deflected, means in actual there is a magnetic field, but according to the Ampere circuital law there is no magnetic field. And this leads to the idea of the displacement current. Okay, first note down this all of you, then we will discuss.
Sir, this is which chapter?
But your voice is not clear, Pawal. What are you saying? Basically, what is this? This is the chapter electromagnetic wave. Electromagnetic waves. Electromagnetic waves.
Okay.
Yeah. So this thing is known as the line integral of magnetic field. This thing is known as the line integral of magnetic field. Line integral of magnetic field. Line integral of magnetic field. Hamza, hello Hamza. Beta, are you getting? Okay. Hamza, you can write in the chat box also. No problem. Okay, Nida. I don't know why you are not responding. Okay, but basically, na, here there is a inconsistency in
Sir, your
Ampere.
voice is breaking.
My voice. Fawaz, is my voice okay or it's breaking?
Sir, in between is break.
Hmm?
Sir, in between is breaking.
My voice is breaking.
Yes,
Okay,
sir.
just a minute. Just wait. Note down. Fawaz, now it's okay.
Yes, sir.
Okay. So if you have any doubt, then you can ask me and write down this. Write down fast.
Done.
Done. Okay. Complete this circuit now. So at X and Y, needle is deflected. But here, the magnetic field is there according to the Ampere's law, but here there is no magnetic field. Okay. So we can say the Ampere's law is inconsistent in this case. Okay. Done. Was completed.
Sir, 1 second.
Hmm.
Sir, 1 second.
Okay. Okay. Have you completed the diagram?
Yes, sir.
Okay.
Yes, done.
Done. Okay. So now so at point X, needle deflected, needle deflected, and according to Ampere's law, according to Ampere's circuital law, there is magnetic field. This is the story of X. At point Y, needle deflected but according to Ampere circuital law, but according to Ampere circuital law, there is no magnetic field, or you can say zero magnetic field. At point Y, needle deflected, but according to Ampere circuital law, the magnetic field is zero. The magnetic field is zero at Y. So there is inconsistency in Ampere circuital law. Ampere circuital law. So basically, earlier we know that due to the current only there is a magnetic field. Due to a magnet or due to the current, there can be the magnetic field. But there is a new concept that we will discuss today. So Maxwell gives the idea that he placed the needle here, and here he is getting some deflection in the needle, means there is some magnetic field, but according to the Ampere's law there is no magnetic field. So he gives an idea of the displacement current. Someone is asking like that, here is a magnetic field, but you are saying that here is no current. Okay, you are saying that there is no current, and earlier we know that current is the source of the magnetic field. That is why he gives another idea of the displacement current. Okay, so now we will discuss the displacement current. Idea of displacement current. So what he said, this is the capacitor and this capacitor is charging. Okay, this capacitor is charging, and this capacitor have the current I. So during the charging of the capacitor, what happens? Current flows in the circuit. Basically, what happens? Charge flow from one plate to the another. Suppose dq charge is flowing from this plate, and that dq charge is finally flowing like this, and finally dq charge like this. This is the dq charge. So here will be some negative charge, here will be some negative charge, and here will be some positive charge. Means there will be the electric field here, there will be the electric field, there will be some electric field here, then again here will be some negative charge, here also there will be positive charge, electric field again increase, here will be negative, here will be positive. So electric field is increasing. Basically, what is happening during the charging of the capacitor, during the charging of the capacitor, in between the plates of the capacitor, electric field is increasing. By here negative charge is increasing on one plate and positive charge is increasing on another plate. So due to this, there will be an electric field, and that electric field is changing. That electric field is increasing, means changing electric field we are getting. Here will be the electric field, and this electric field will be changing electric field. changing electric field. So Maxwell said that due to this changing electric field, there is another type of current. There is another type of current different from this current, known as the displacement current. Displacement current. Okay. Displacement current. I suffix D. I suffix D is the displacement current. And what is the cause of the displacement current? Changing electric field. Changing electric field, or you can say changing electric flux. What is the electric flux? Number of electric field line crossing an area perpendicularly. So these electric field lines crossing this area of the cross section of this plate perpendicularly, you can say that displacement current it is due to the change in electric field or change in the electric flux. So we can say that now. After that, what Maxwell said? Maxwell said that Maxwell said that not only current produces the magnetic field, but a changing electric field can also produces the magnetic field. A changing electric field in vacuum or free space also produces the magnetic field. Basically what is happening here, charge is increasing on this plate, and here also positive charge is increasing, here negative. Due to the increase in the charge, electric field is changing or electric field is increasing. Electric field is changing basically. Due to the change in electric field, there is a magnetic field that I have told you that time. Here is a deflection of the needle deflected. Why this needle deflected that time? Because in between the plates of the capacitor, if you will say that here you can say that there is no current in between the plates of the capacitor. So according to the Ampere's law, there should not be any magnetic field here. But what is happening here now? When you will see here, due to the change in the charge on the plates of the capacitor, there will be some changing electric field, and changing electric field produces the magnetic field. This is said by the Maxwell. Earlier we have studied changing magnetic field produces the electric field according to the Lenz law, according to the Faraday's law of electromagnetic induction. There what we have studied, whenever there is a change in the magnetic flux, should be an EMF induced. Okay, so what is the magnetic flux change? When you are changing the magnetic field, means you are changing the magnetic flux, and when you are changing the magnetic flux, there will be the EMF, and that EMF leads to the electric field. So we already knew that changing magnetic field can produce the electric field, but Maxwell said that changing electric field can also produce the magnetic field. So basically, this current in the circuit is basically known as the conduction current. Okay, current in the circuit is known as the conduction current. So what is conduction current? Conduction current is basically I. This I is the conduction current. Okay, so talking about the conduction current, so basically your conduction current will be simply current in the circuit, and this conduction current you can represent it by I suffix C. Now there is another current, displacement current.
Sir, what is electric field?
What is electric field? But
Yes.
the electric field, you can say the space around a charge in which if another charge is entering, that charge will experiences the electric force. Okay, I am explaining what is electric field.
Okay.
Basically, this suppose this is a charge, na.
Yes.
So suppose here is any charge, suppose Q naught. Okay, and due to this charge, na, due to this charge, uh, this charge Q naught will experience a force. Will experience a force. Suppose this is experiences an attractive force. So according to the Coulomb's law, there will be the force between the two charges, and that force is given by K Q into Q naught divided by the distance square. Okay. So basically, electric field is force on a charge divided by the charge. So basically, from here you will get E is equal to KQ by R square. This is the formula you will get. So this is the formula, and for the definition, you can say the space around the charge in which another charge experiences the electric force. Okay, so displacement current. What is displacement current? This is very important concept and new for you also. Displacement current is represented by ID. So a displacement current, a current due to changing electric field or electric flux. A current, earlier what I have told you, what is current? Basically, I have told you current is charge. Whenever there is a motion of the charge, there is a current. Earlier we know that now. What is current? Current is charge divided by time. In earlier chapters, we knew that what is current? Current is charge divided by time, dq by dt. But they are saying there is another type of current, that is displacement current. This current is due to the changing electric field. Earlier we know the current is due to the motion of the charge. So a current due to changing electric field, changing electric field or electric flux, or electric flux, or electric flux. And this conduction current is given by simply dq by dt, we know that. But this displacement current is founded by the Maxwell and given the formula epsilon naught T phi E by dt. What is phi E? Phi suffix E is the electric flux. Is the electric flux. What is the electric flux? Number of electric field line crossing an area perpendicularly. So formula of the electric flux will be electric field into area into cos theta. Theta is the angle between the electric field vector and the area vector. We have discussed the magnetic flux now. Like that, there is an electric flux also. Okay, so so it is found that at point x and at point y, experimentally it is found that at point x and at point y, the magnetic field value is same. Experimentally it is found that at point x and at point y, the value of the magnetic field is same. So the conclusion we made that the displacement current and the conduction current both are equal. Okay, so I am writing here at point x and y, the magnetic field is same. This is found experimentally. So it implies that if the magnetic field is same, if the magnetic field is same means this current is producing the magnetic field, and here is the displacement current that is producing the magnetic field. Means you can say that the conduction current, what is the conduction current? The current in the wire is known as conduction current, and current in the vacuum is known as displacement current due to change in electric field. Both are equal. Okay, so both are equal. Okay, so write down. Fawaz made this diagram.
Yes, yes, sir.
This is conduction current, so I will represent conduction current with I suffix C. And conduction current is flowing in wires only. Completed. Okay.
So done, sir.
Okay. Just wait. Hamza, are you taking screenshots?
Yes, sir.
Okay. So displacement current is due to change in the electric field or electric flux, not due to the motion of the charge, not due to the motion of the charge, changing electric field. Okay. Was completed.
Yes, done, sir.
Okay. Okay, so now all these things I think will be clear. Here is some electric field, and this electric field is changing. Why this electric field is changing? Because charge on the capacitor is increasing. Charge on capacitor increasing. Charge on the capacitor is increasing. Okay. So now see. Suppose this E is the electric field. What is this electric field? Electric field is in between the plates. In between the plates, there is an electric field, and that electric field is changing. So E is the electric field between the plates. Electric field between plates of the capacitor. Between plates. Okay. Can anyone tell me what is the electric field between the plates of the capacitor? Is sigma is the surface charge density of the capacitor or plate. Sigma is the surface charge density. What is the value of the electric field between the plates of the capacitor? If sigma is given. Very good, Nida. Very good. Well done. Very good. So between the plates of the capacitor, the value of electric field is equal to sigma divided by epsilon naught. Sigma is the surface charge density, and epsilon naught is the absolute permittivity of vacuum or free space. And what is sigma? Sigma is charge on the plates of the capacitor. I am supposing charge on the plates of the capacitor as Q. Q is the charge on the plates of the capacitor. Sigma is charge divided by area. Charge divided by area. Q, suppose Q charge is on the plates of the capacitor. Okay, Q is the charge on the plates of the capacitor. At any instant of time, suppose Q is the, here is plus Q charge, and here is minus Q charge at any instant of time. And with respect to time, this charge is changing. This charge is changing. So Q is the charge, A is the area of the plate, A is the area of the capacitor plate. So electric field we can write, electric field value we can write as sigma can be written as Q divided by A, and this becomes Q A epsilon naught, Q divided by A epsilon naught. Okay, if I want to write the magnetic flux, not the magnetic, electric flux through the plate, through any of the plate, electric flux through any of the plate. What is the formula of the electric flux? Phi E dot A or EA cos theta. Electric flux is E dot A. This is equal to EA cos theta. Okay, so electric field is in this direction. Electric field is in this direction, and if you will take the area vector, then direction of the area vector will also be in this direction. Area vector will also be in this direction. Okay, so here there is no space, but you know that area vector is perpendicular to the surface. So there is a 0-degree angle. There is 0-degree angle between the electric field and the area vector. That is why your cos theta is cos 0. So your electric flux will be given by EA only. What is E? Put the value of E. This is the E. Q divided by A epsilon naught. Q divided by A epsilon naught. So electric flux is Q divided by A epsilon naught. Now see, area of the plate is constant. Area of the plate constant. Epsilon naught will be constant, but charge is changing. Charge is changing. So we can differentiate this with respect to time. This will become d phi E by dt, and this will become 1 upon A epsilon naught dq by dt. Okay, this is dq by dt, and A epsilon naught dq by dt. Basically here this is EA na, E, and this, oh, 1 minute, I have written here E is Q by A into epsilon naught multiplied by A also na, and A will be cancelled out. So Q by epsilon naught will be the answer here. Okay, Q by epsilon naught. Phi E will be Q by epsilon naught. Okay, so here there will be no A. Okay. Now what is dq by dt? Dq by dt is the current. Dq by dt is the current. So you can write this dq by dt as displacement current is equal to the conduction current. So this will be the displacement current. So now you can write d phi E by dt into epsilon naught is equal to the displacement current. Okay, so this is the formula for the displacement current. Epsilon naught or d. What is d phi by d? What is phi E? Phi E is basically the electric flux. Phi E is basically the electric flux. Phi E is the electric flux. Okay, note down. Okay, so done. Okay. Fawaz, have you completed this diagram?
Yes, sir.
Okay. Epsilon 0 or epsilon naught is the absolute permittivity of free space. Absolute permittivity of free space or vacuum. Phi E is the electric flux. Phi E is the electric flux. And ID is the displacement current. ID is the displacement current. Now, in the beginning, I have told you there is some inconsistency in the Ampere circuital law. So if there is inconsistency, so there should be the modification in that law. So we will discuss now modification of Ampere circuital law. Modification of Ampere circuital law. Completed
Done,
all
sir.
of you? Completed? Okay. Hiba, what is your name? Nida. Completed, Nida? Okay. Very good. Hamza, taken the screenshots?
One minute.
Better tell me if you are not able to take the screenshots, okay?
Done.
Now there is a modification in Ampere circuital law. If that law is inconsistent, okay, and that is done by the Maxwell, okay, that is done by the Maxwell. So modification of Ampere circuital law. Ampere circuital law. So what is the modification basically? Two plates of capacitor, one is this, another is this, and this is the wire, okay, this is a wire like this, and this is a free space. So here in the free space there is a current called displacement current, and in the wire there is a current called conduction current. Okay, now Ampere circuital law, earlier what we have written earlier, what was the Ampere circuital law? Line integral of magnetic field is equal to mu 0 into current. Now we will write the line integral of magnetic field along a closed path is equal to mu naught times of the conduction current plus displacement current, and this can be written as V dot dl is equal to mu naught times of conduction current is I simply, and what is displacement current? Epsilon 0 d phi E by dt, So basically, finally, this is the modification in Ampere circuital law, and just a minute. Okay, now we can. So this is basically the modification, and this is now known as the Ampere Maxwell law, because first it is given by the Ampere and this is modified by the Maxwell. That is why it is known as the Ampere Maxwell law. Ampere Maxwell law. Ampere Maxwell law. Okay, so write down this. After that, we will solve one numerical.
Done, sir.
Okay. So there are two notes points. I'm gonna take the screenshots. Okay. Two note points for conductor. Displacement current is equal to 0. Another point. Displacement current exists in displacement current exists in dielectric or insulator. Dielectric or insulator. So I have told you that there will be no displacement current in a wire or conductor, and it exists in the dielectric medium or some insulator. So write down this also, then we will solve the numerical. This is from NCRT. Okay. Now we will solve this question. They are saying a parallel plate capacitor shown in this figure made up of circular plates. These are the circular plates, each of radius 6 centimeter. Radius 6 centimeter has a capacitance of 100 picofarad. 100 picofarad, and the capacitor is connected a 230 volt AC supply. Okay, here a supply of 230 volt is there with an angular frequency of 300 radian per second. First part, what is the root mean square value of the conduction current? Root mean square value of the conduction current. Is the conduction current equal to the displacement current? They are asking. In the third part, they are asking determine the amplitude of the magnetic field at 3 centimeter from the axis between the plates. Okay, so basically, what things we it is given in the question. First thing is here this radius is given. Radius is given as 6 centimeter. So I am writing here. So basically, first capacitance is given. I will not write on the diagram. So capacitance is given as 100 picofarad, and the capacitor is connected to 230 volt AC supply, means the peak value of the voltage is given 230 volt, and omega is given as 300 radian per second, 300 radian per second, and radius of the plate, like this is the radius of the plate, this is the R, suppose this is R, this R is given as 6 centimeter, R is given as 6 centimeter. So what will happen in this case? This is so in the wire there will be the conduction current. In the wire there will be the conduction current, but in between the plates, there will be the displacement current, and we know that the conduction current is equal to the displacement current. Okay, conduction current is equal to the displacement current. So they are asking what is the root mean square value of the conduction current, root mean square value of the conduction current, A part. So they are asking root mean square value of the conduction current. Okay, so first calculate the maximum value of the current, that is peak value of the current. Peak value of the current is equal to voltage divided by XC. Here this is basically a pure capacitive circuit, so here will be XC, means capacitive reactance will be there, and XC is given by 1 upon omega C. XC is given by 1 upon omega C. Okay, so we will calculate first XC. 1 upon omega is given as 300. What is C? C is given as 10 picofarad. 1 picofarad is equal to 10 to the power minus 12 farad. So from here we will get XC. Okay, so now we will calculate I naught. I naught is equal to V naught. V naught is 230 by XC. XC is 1 upon 300 into 10 to the power minus 12. When you will calculate this I naught value, you will get 69 root 2 into 10 to the power minus 7 ampere. So this will be the value of this will be the peak value. This will be the peak value of the current. What is this? Peak value of the current, or maximum value of the current, or amplitude of the current. Peak value. They are asking root mean square value of the current, means IRMS they are asking. IRMS is given by peak value divided by the root 2. What is the peak value? 69 root 2 into 10 to the power minus 7 divided by root 2. Root 2 and root 2 will be cancelled out. So your answer will be 69 into 10 to the power minus 7 ampere. Second part, B part. Is the conduction current equal to the displacement current? Of course, we know that conduction current equal to the displacement current. Conduction current is equal to the displacement current. What is the conduction current? Basically, this is the conduction current. Okay, the current, this is basically the current in the wire, and current in the wire is known as the conduction current. So conduction current is 69 into 10 to the power minus 7 ampere. So conduction current is equal to the displacement current here. This part is also finished. Last part. They are asking determine the amplitude of the magnetic field at a point 3 centimeter from the axis of the plate, between the plates. Okay, so basically C part, one plate of the capacitor is this, another plate of the capacitor is this. Okay, now this is the capacitor. They are asking, this is the suppose axis. Okay, this is the axis, and they are asking at a point which is 3 centimeter above the axis. Here we have to find the magnitude of the magnetic field. Okay, so what we will do, we will take an Amperian loop here. We will take an Amperian loop. We will take a loop and we will apply the Ampere circuital law. What is Ampere circuital law? We will apply modified Ampere circuital law, that is Ampere Maxwell law. Okay, V dot dl is equal to mu naught times of the conduction current plus the displacement current. Conduction current plus the displacement current. Okay, so this will be v dot dl is equal to mu naught times of the conduction current here in the free space or in between the plates. The conduction current is zero. There will be only displacement current. There will be only displacement current. Okay, there will be only displacement current. Now this you can write v into 2 pi into radius of this loop, that is 3 into 10 to the power minus 2. I think you have not got it. Beta, we are applying the Ampere's Maxwell law here. Okay, conduction current here will be zero because I have told you conduction current will be in the wire only. Now this loop, this closed loop, from this closed loop, how much will be the current? That is this current. This is the displacement. We can say that this is the displacement current through loop. Okay, through loop. Now there is a problem. This loop have the 3 centimeter radius, but in whole of this area, if we are considering, if we are considering a loop, here if we are considering a loop like this, if I am considering, so in this area, the current will be this current, because this is the total current. Okay, so current in pi r square area is equal to this. So unitary method we will apply. So in I can say in pi into 6 square area. What is the pi into 6 square area? This. Okay, this area is pi into 6 square because radius of this is 6 centimeter. Okay, so in pi into 6 square, the displacement current is 69 into 10 to the power minus 7. This will be 69 into 10 to the power minus 7 ampere. In unit area, between the plates, the current will be 69 into 10 to the power minus 7 divided by pi into 6 square ampere. This will be the current. Now we want to find the current in area pi into 3 square. So in pi into 3 square area, simply we will multiply this pi into 3 square here. This is pi into 6 square. This is pi into 3 square. And finally, the value of the current, displacement current through 3 centimeter radius or area is equal to, we will get 69 into 10 to the power. Okay, so this pi and pi will be cancelled out from here. This pi and pi will be cancelled out. And here will be 3 3 is 9 and this is 6 6 is 36. Here will be 69 by 4. 69 by 4 into 10 to the power minus 7. This will be the displacement current through the area of, this is the displacement current through loop. Okay, this is the unitary method. Now we can use this equation, B dot dl is equal to mu naught into id. So B dot dl So this is, we have B dot dl is equal to mu naught into id we have. So we can, this magnetic field is constant, I have told you, and dl, close of dl, we can write as mu naught into id. This can be written as v into 2 pi into radius of the loop. Radius of the loop that we have chosen, this is 3 centimeter square, 3 centimeter. So in 1 centimeter, 10 to the power minus 2 meter. So you will write here 3 into 10 to the power minus 2. Okay, 2 pi r. This is the length, and is equal to mu naught. And what is id? Id is this 69 by 4 into 10 to the power minus 7. Okay, now put the value. This is v into 2 pi into 3 into 10 to the power minus 2. This is mu naught is given by 4 pi into 10 to the power minus 7 multiplied by 69 by 4 multiplied by 10 to the power minus 7. Finally, when you will solve it, you will get the value. This is your homework. Okay, so write down. And basically, if you want to copy this question, then copy. Otherwise, in exercise of chapter number 8, exercise chapter number 8, 8.2 question will be the this question. Okay, so I think there is no requirement. So this is a question from exercise chapter number 8, electromagnetic waves. Electromagnetic waves. Okay, you will get the question and you should write the answer only, all of you. This is a good question, I will say. Okay, Hamza and Fawaz and Nida.
Sir, can you show the question? I will write it.
You will write the question. Why
Yes,
you are
sir.
writing? It is already given in NCERT.
Sir, it will be in these notes only, right? That's
Okay, that's fine. You can write it if you want. Today's lecture is very basic, na? Means I have not talked about the electromagnetic wave. This is just the basic introduction about this chapter. So in the next lecture, we will discuss how the electromagnetic wave can be generated. Nida, got it? This question?
it's done, sir.
Okay. This question is third part, especially I will give 1 star to third part. Why? Because third part is important. Okay. There will be a confusion to calculate the displacement current through the area of 3 centimeter radius. I know that. Okay. Written the question? Nida, completed? Hamza? Okay. So write down the answer now. So especially focus on the third part, and all other parts are very easy. You can do easily. I know. In third part there will be slight confusion maybe, and there you will apply the unitary method. Unitary method. I think you should know. What is unitary method? Okay, Fawaz, completed.
Done, sir.
Okay. Hamza, have you taken the screenshot? Scroll down.
Done.
Okay. So basically, na, this is these are yellow color things are the plates of the capacitor. Don't think this is something else. Okay. I have not made the whole circuit. This will be like this. Okay. Here will be your AC source. These are the plates of the capacitor. Scroll down, Fawaz.
Yes, sir.
Okay, Hamza, take the screenshot.
Sir, can you scroll little up?
Fine.
Yes, sir.
Hmm. Okay. Better do the calculation by yourself. Okay. This is 69. What you will do now, this 2 pi and this cancel out. Okay. And here is 3 and this will cancel out with this. 3 to the 6, 3 3 the 9. And here will be, this will become basically, this is V into 10 to the power 2. Okay. This is V into 10 to the power 2. Here what you have? 2 into 10 to the power minus 14. 2 into 10 to the power minus 14. This is 2. 10 to the power minus 7, 10 to the power minus 7, 10 to the power minus 14, and 23 by 4. 23 by 4. This will be cancelled out. Okay. This will become 23 by 2. So basically the magnetic field will be here 10 to the power minus 2, and here it will go. So it will become 23, 2 ones are 2, and 2 ones are 2. This is 11.5 into 10 to the power minus 12. This will be, I think, the answer. Tesla. Okay. So in this way you can find the answer. Just check it by yourself once. Okay. Done, all of you? Okay.
Sir, can you say how did you got 3 into 10 raised to minus 2?
This na you are saying this
Yes, sir.
this is basically the radius. The radius is given as 3 centimeter. I have converted it into meter. And
Okay.
area you will calculate pi into 2 pi r. 2 pi into r. This is the perimeter. 3 into 10 to the power minus 2. Basically what we are doing now, this is the loop. So b into length of the loop. What is the length of the loop? Perimeter of the loop. Perimeter of the loop is 2